Hi class. In this lecture video here, we're going to talk briefly about section 2.1, which is about counting. And what this chapter talks about is how we can use something called the pigeonhole principle and how it leads to precision through estimation. Basically, how you can use this pigeonhole principle to answer or solve some really, really cool questions. Like, for example, the textbook asks, are there two humans on planet Earth that have the exact same number of hairs on their body? Like, how would you even begin to answer that and prove it? And it turns out that there are, and we use this pigeonhole principle to prove it. So I'm going to do a problem that's slightly different than the ones presented in the textbook to illustrate this. All right. So, anyways, what is this pigeonhole principle? All right. So the pigeonhole principle is a fundamental concept in combinatorics and mathematics. It states that if more items are placed in fewer containers than the number of items, so there's fewer containers than the number of items, at least one container must contain more than one item. So mathematically, it looks like this. If you have n items are distributed among n containers, so that in this case, the number of items is greater than containers. Like, for example, if you have 5 pigeons, but only 4 holes, okay, four pigeonholes, then at least one container, in this case, at least one pigeonhole must contain more than one item. That's it. That's all it says. And like intuitively, that makes sense, right? Like there's no way to have 5 pigeons go into the holes unless unless 2 pigeons go in one hole. Like it makes sense. So let's use this pigeonhole principle to answer this question. Why does every person have many temporal twins on Earth? Okay, so what is a temporal twin? That is people who were born on the same day and will die on the same day. That's what I mean by this kind of a morbid example. All right. Like, does that make sense? I don't know. So let's use me as an example to show this and talk about the pigeonhole principle as a result. So, getting older, I was born on February 2nd, 1982. All right. So the question is this. Obviously, in the whole world, okay, I was not the only person born on February 22nd, 1982. Okay. But basically, what I'm asking is this. So I was born that day. So we're in a bunch of other people. Is it likely, okay, that somebody born the same day as me is also going to die the same day as me? All right. So first off, what we have to do is let's estimate the number of people who were also born on that day. And it's really interesting how to do this, okay? So it turns out the global population in 1982 was 4.6 billion people, all right? It turns out the birth rate in 1982 was 25.5 people per 1,000. And this is just statistics you can pull up, okay? I'm not making any of this up. So what you can then do is figure out the total number of births. So in 1982, total births were you take 4.6 billion people, you multiply it by the birth rate, okay, of 25.5 over 1,000 people, and you get roughly that year in 1982. Remember, this is worldwide. This isn't just in the United States. This is across the entire globe, okay? There were roughly 117.3 million people born, okay? But that's throughout the whole year. So now February 22nd is just one day out of the year. So we're just going to assume roughly births are uniformly distributed across days. That may or may not be true, but what that means is roughly births per day. If you take the 117.3 million and divide it by 365 days, there were roughly, okay, 320,000 people born, okay, on February 22nd, 1982, okay, and across the entire globe. That's a lot, right? So that means there's 320,000 people who share not only my birthday, but my birth year. Okay. Not all those people are still alive. All right. But, that's just roughly the number. Okay. So now the question is, I'm still alive, obviously. So why is it that I'm likely to have temporal twins? At least one other person who have been born, who's still alive right now, that when I die, hopefully many, many years from now, many decades from now, will die the same day that I do. All right. So this is how we're gonna look at it. Okay. So there's roughly 320,000 people were born the same day I was. Those people will all die. Okay. It's unfortunate and sad. They will all die. So let's just assume a 100-year period. starting in 1982. So a little bit of assumption, right? The life expectancy for these people is well under 100. So maybe a handful of them will live, a couple hundred might live to be over 100 years old. But let's just assume a 100-year period. Okay. What that means is from the day I was born till the day I die. Okay. Which would, assuming a 100-year period, which means, I could die between now, the day I was born, and 100 years from the day I was born, which would be, 2082. Okay. February 22nd, 2082. It turns out that if I live for a 100-year period, or we assume a 100-year period, that's 36,500 days, a few more because of leap years in there. Okay, so that means I'm going to get to live 36,500 days. All right. So if there are only 36,500 days of life, okay, and there are 320 people, let's connect the concept of large numbers of people born on the same day with a simple conclusion. Okay. Given so many born on the same day, okay, because there's only 36,500 days that people could die. Okay. So, like, for example, what I mean is somebody could have been born on February 22nd, and then, God, it's really sad, but then died on February 22nd or 23rd, 1982. Okay. All the way to 100 years from now. It's statistically likely that at least two will die on the same day to similar life expectancy. So, like, here's the pigeonhole principle. If n items are distributed among m containers, and n is greater than m, then at least one container must contain more than one item. So from my perspective, if you consider the containers to be the days of life, okay, from day one all the way to 100 years now, there's 36,500 possible days I could die. Okay. And if you put people, all right, and you're going to put these people into these buckets, right? Because there are people within there who died on the first day of life, second day of life, and so on. Okay. There's obviously more people than days, or in this case, containers, to die. So then for Matt, from my perspective, when I go to die, this is really terrible, but when I die, I will die on the same day as someone else born on the same day as me. Because if you spread out all these people into these containers of the possible days to die, there's more people than possible containers. So, you know what? At least some of those containers are going to contain more than one person. And when I go from my perspective, all the containers will be full, and I will die at least in the same day as somebody else. And it's really interesting like when you in the textbook will talk about like why, there are at least two people in this world who have the same amount of hairs, on their body, and it's the same idea with the pigeonhole principle. All right, so I hope this morbid example, and I hope I live to be more than 100, but I hope this example illustrates, the pigeonhole principle and how you can use it to, answer a problem like, why do people have temporal twins?